So today we are talking about arithmetic series, and as you may guess, this is related to arithmetic sequences. But there's a distinct difference between a series and a sequence, so we want to look at this first example to kind of differentiate between the two. So in this example, we have chairs set up for a meeting. In the first row, there's 4 chairs. In the second row, there's 5. Third row is 6, 7, and so on. So before we would have written this as a sequence as 4, 5, 6, 7, where your common difference is 1. This question is then asking us about the 20th row. Well, using the explicit formula for an arithmetic sequence, we could have figured out how many chairs would have been in the 20th row. But this question is asking us something different. It's asking us how many total chairs are there going to be. So we could have used the formula to figure out how many would be in the 20th row, but now we want to figure out, I need to add up 4 plus 5 plus 6 plus 7 plus 8 all the way to plus 19 plus 20 to figure out how many total chairs there are in this meeting. So the difference between a sequence, which is just the ordered list of numbers, and a series is adding up all the terms. So it's the indicated sum of the terms in a sequence. So a series is the indicated sum of the terms in the sequence. So in this chair example case, 4, 5, 6, 7, and so on would be the sequence, and the series would be 4 plus 5 plus 6 plus 7 all the way until we got to plus 19 plus 20 in this case, if we were trying to figure out how many are in 20 rows. So just some vocab to go over. The difference between a finite and an infinite sequence has to do with, is this sequence going to go on forever or not? So if you think about the difference between finite and infinite, finite is limited, where infinite, think of infinity, it goes on forever. So a finite sequence has a distinct first term and last term. So there's only, say, 20 terms, or 10 terms, or 3 terms. It has a distinct first term and last term. So there's only a limited number of terms. So for example, the sequence 6, 9, 12, 15, 18, there's no comma dot 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 after it, so that means this sequence only has these 5 terms. An infinite sequence, on the other hand, has no end. But we could write a sequence 5, 10, 15, 20, but then if we do this dot dot dot, that means it's going to go on forever. I'm going to keep adding 5 to each term forever, all the way into infinity. So now a finite series is the sum of a finite sequence. So this means I'm only adding up a certain number of terms. For example, I would add 6 plus 9 plus 12 plus 15 plus 18. So a finite series is just the sum of a finite sequence. So in this case, the finite series that goes along with the sequence is 6 plus 9 plus 12 plus 15 plus 18, which gives you a total of 60. So we can evaluate that finite series. An Infinite series, on the other hand, we cannot determine the sum. So this sum cannot be determined. Because if you think about it, we're adding, in this case, 5 plus 10 plus 15 plus 20 plus 25 plus 30 plus 35 plus 40, etc. These numbers are going to get huge, and we're going to end up adding huge numbers together, so there's no way for us to actually evaluate what that number is going to be. So we cannot figure out what this sum is, an infinite arithmetic series. But we can determine what a finite series, what that sum is going to be using this formula. So first I just want you to think for a minute. If you want to pause the video to think about this, I want you to think about how would you add up all the numbers between 1 and 100. So how would you add 1 plus 2 plus 3 plus 4 all the way to plus 96 plus 97 plus 98 plus 99 plus 100. So go ahead and think about that for a minute. So it turns out there is a formula we can use to add a sequence of numbers like this together. So if you notice here, this is arithmetic. Your common difference is just 1, and you're starting at 1. So we say the sum of a finite arithmetic series that has, so from one term to the next, has a common difference. We use S sub n equals n over 2 times a sub 1 plus a sub n. So what do all these variables mean in here? S sub n just turns out to be the sum of m terms. So what do you get when you add all 15, let's say, terms together? So n is just the number of terms you're adding together. A sub 1, just like it was in our formulas before, it's the first term. And a sub n is the last term. So because this is finite, it has an end, so it has a last term. For example, in the 6, 9, 12, 15, 18, there are 5 terms, so n would be 5. A sub 1 would be 6. A sub n would be 18. So let's go back to this 1 plus 2 plus 3 plus 4 all the way to 100. How could we add those up without actually having to calculate all of that? Even with a calculator, this would take a long time. So using this formula, we say S sub n is n over 2 times the sum of the first term plus the last term. So the first thing we have to figure out, how many terms are there? What's the first term? And what's the last term? Once we know those 3 things, we can just plug and chug into this formula. So I'm adding up 100 different numbers, so there's going to be 100 different terms. The first term is 1. The last term is 100. So plugging all of that into the formula, I would have 100 over 2 times the first term plus the last term. So that's 50 times 101, which gives me a total of 50, 50. You might have been able to determine that a different way, using a different strategy, but this formula is going to work for all of these types of problems. for any arithmetic series you're trying to add up. So now there's this specific type of form we use called summation notation, which is just this quick way to write a sum without having to write out, for example, 1 plus 2 plus 3 plus 4 plus 5. It's kind of this quicker way to represent what the series is. So it's a shorthand way to represent a series. And we do it using limits. So these limits are just going to tell us where to start and where to end. So if it's finite, it's going to tell you, okay, I want to add the third term to the 8th term. So it kind of tells us where in the sequence which terms we're trying to add together. So limits just mean the least and greatest values for n. So to write a series in summation notation, we use this Greek letter to kind of represent the sum. So there's different parts of what this kind of notation looks like. The first part is below this sigma sign. We say n equals. N equals some number is going to be our lower limit, or the least possible value for n. So for example, if we wanted to add only the 5th term to the 12th term, 5 would be our lower limit. It's kind of what term we're starting at. Then up top, we plug in the upper limit. And that upper limit is just the greatest value for n. So again, if we're adding the 5th through the 12th term, 12 would go up here. It's also important to note that if you were doing an infinite series, so it goes on forever, there is no upper limit, so we would use the infinity symbol up here if it goes on forever. So in an infinite series, we're going to use that infinity symbol as our upper limit. The last part of this notation is whatever we put right here. This is just the explicit formula for the sequence. So how can we figure out what each term is that we need to add together based on what n is? For example, we're going to look at this series, 3 squared plus 4 squared plus 5 squared plus 6 squared plus so on until we get to 108 squared. Now, this is not arithmetic, but we can still write it in summation notation. You can write most series in summation notation. It doesn't necessarily need to be arithmetic. So we're going to set up our summation notation. We need to do 3 things. What's the lower limit, what's the upper limit, and what's the formula? Now, looking at this first term doesn't necessarily have to be n equals 1. It might make more sense if this was a series that was going on, but now I'm just starting from 3 to 108. So if the explicit formula is just n squared, I take n, I square it to get all of these different terms in the sum. I can just say I'm going to start at 3 and I'm going to end at 108. So I have my lower limit, upper limit, explicit formula. So this tells me if I'm operating on the explicit formula n squared, I first plug in 3, then 4, then 5, then 6, then 7, then 8, all the way until I'm plugging in 108, which is exactly the formula I have here. So then if you were actually trying to evaluate this, you would need to know how many terms there are. So the number of terms is always the upper limit minus the lower limit plus 1. So upper limit minus the lower limit plus 1. So if you had the sequence going from 1 to 100 like we did before, it's easy to tell there's 100 terms in there. In this case, if we're starting at 3 and going to 108, the number of terms, I'm going to do 3, 4, 5, 6, all the way until 108. That gives me 108 minus 3, which tells me how many numbers are between these two. But then I have to add 1 because I'm also including 3 and 108. So in this case, I get 106 terms. So that's going to be important when we're plugging into the formula. In this next example, this one is arithmetic because you see we have a common difference of 4. So the first thing we're going to do is write the explicit formula using the formula we used last time. So the first term plus n minus 1 times the common difference. So this gives me 4n plus 3 as the explicit formula. So I'm going to write my summation notation. The explicit formula is 4n plus 3. It's really important that I put the explicit formula in parentheses, especially if it's more than one term like that. So now I need to write my lower limit and my upper limit for this. So my lower limit is if I plug in 1, I get 7. So I'm starting at the first term. Notice how we have the 3 dots at the end. That means this arithmetic series goes into infinity. It's infinite series, so we're going to put an infinity symbol up here. So we come up with the explicit formula, then figure out which terms we're adding together. One key idea to remember here is if the explicit formula for a sequence is linear, like y equals mx plus b, that's what this form is in. The sequence is arithmetic. And the slope of the linear function is the common difference. So that's something to keep in mind if you're ever trying to determine if something is arithmetic, so that you can use the arithmetic series formula. You first need to determine if it's linear or not. So for example, in this first one, this is linear. Think y equals mx plus b. That means it came from an arithmetic sequence where the common difference was 5. So now we're going to actually evaluate what this sum is using the formula. So S sub n equals n over 2 times the first term plus the last term. So we need to know 3 things: n, a sub 1, and a sub n. So this one's pretty easy to figure out how many terms there are. You're adding from the first term to the 70th term. So there's 70 terms. Or you think upper minus lower is 69, plus 1 is 70. The first term would be if I plug in 1 to this explicit formula. So 5 times 1 plus 3 is 8. So that means this sequence starts at 8, then it goes to, I plug in 70. So 5 times 70 plus 3 gives me 353. Once I know these 3 things, those are the 3 key things, I can plug everything in. So 70 over 2 times 8 plus 353, plug 35 times 361 into our calculator, we should get 12,635. So using this formula saves us a ton of time, because otherwise we would have to plug in 1, plug in 2, plug in 3, plug in 4, all the way to 70, and then add all of those together. So that formula saves us a ton of time if it is in fact arithmetic. Looking at this second one, this is not arithmetic. This is not linear. It's actually a quadratic. So we can't use this quick short formula. This only works with arithmetic series. This, not arithmetic. That doesn't mean we can't still figure out what the sum is. It goes from n equals 1 to 7. So that means I'm really only adding 7 different terms. Not too bad. We can just figure out what each of the 7 terms are and then add them all together. So if I first plug in 1, 1 would be 1 minus 1 squared. Plug in 2, plug in 3, plug in 4, plug in 5, plug in 6, and plug in 7. That's all this is telling us to do, is plug in all the numbers between 1 and 7 into the formula, add them all up. If you do that, you would get 0 plus 1 plus 4 plus 9 plus 16 plus 25 plus 36. Add them all up, you should get a sum of 91. So again, important to remember, if it's arithmetic, use the formula. If it's not, you have to write it all out. Last example is going back to the similar example to the one that we started with. You have a 20-row theater. The number of seats in each row increases by 3 in each row, starting with 18. So it's going to be 18, 21, 24, 27, etc. for 20 rows. And we have to figure out, okay, well, how many total chairs are going to be in here? So we're first going to write the arithmetic series, which we can just write as 18 plus 21 plus 24 so on. But let's write it in summation notation. So in order to do that, we first need to know the explicit formula. It is arithmetic, so I can write it as 18 plus n minus 1 times the common difference. So that's 18 plus 3n minus 3. Our explicit formula is 3n plus 15. So this series, our explicit formula is 3n plus 15. We're adding up all the way from row 1 to row 20. So that's what it's asking us to do in the first part. To find how many total seats, we just need to use the sum formula because it is arithmetic. It's going up by 3. So n over 2 times the first term plus the last term. Well, we know there's 20 rows, so n is going to be 20. We know the first term is 18. The last term, we just have to find out if we plug 20 into this explicit formula, we would have 60 plus 15, 75. 10 times 93 gives us 930 seats. So again, you can use that formula when it is arithmetic. So now I want you to pause and try the 6 checkpoint questions that follow in the notes. And here are the answers to those checkpoint questions. The first one, your upper limit is 7, your explicit formula is 5n. Number 2 is a little tricky. You have to kind of do some guess and check here. You know the first term is 9, so if you plug in 1 to the explicit formula, you should get 9. So you can eliminate some of these right away, because when you plug in 1, you do not get 9. When you plug in 2, you should get 12. So you can eliminate some of these where you would not get 12 when you plug in 2. So now you're left with C and F. So now you just have to figure out, are there 15 terms or are there 16 terms? So you're trying to figure out, is 51 the 15th term or the 16th term? Well, you already know, based on process of elimination, that 3n plus 6 is your explicit formula. So you're trying to figure out 51 is which term number in the sequence. Turns out it is the 15th term, so that means your upper limit had to be 15 because that is where it stops. Number 3 was 553. The tricky part here is you have to figure out what term in the sequence 72 is. So when you plug it in and find that out, you find that n is 14. And that should help you plug into the formula. For 4, the grade on the final test is 86. The total score is 441. The sum of the sequence is 5,920. Number 6, similar to the one we previously did, is 2,193 total seats. I'm going to go through example number 3 if you still need clarification. Otherwise, check your answers and make sure you can do all of these types of problems. For 3, To plug into this formula, you need to know those three things still. How many terms? The first term plus the last term. Right away, you know the first term is 7, the last term is 72. To figure out what term number 72 is, use the explicit formula for an arithmetic. First term, common difference is 5 times n minus 1. So that's 5n plus 2. Where does 72 fall in that? It's the 14th term. So you would just plug in 14 for n, and you will get that answer.